Okay, we're back with a video regarding the second derivative test. So again, we normally think, oh, the second derivative test performs like the first derivative test. But that's not the case at all, actually. The second derivative test uses the second derivative to help determine relative maxes and relative mins. Okay, so it's another way to find out whether a critical point is a relative max, a relative min, or neither. So that's our charge right here. We have the basic function h of x is equal to x cubed minus 6x squared plus 2. Find all critical values of h and determine if each value is a relative max, a relative min, or neither. And let me just state right now that this actually is a topic which is important, and you can absolutely use it, but it won't necessarily be tested on the AB exam. I have seen it come up on the BC exam. It's part of calculus. It's something that you might as well know because it's another way to get about the answer. And you can do this basically avoiding the sign charts. So if you're not a big fan of that, then this is another way to get the max or the min. So here we go. We want to find the critical values. We know critical values occur when the first derivative is equal to 0. So let's get the first derivative. All right, we need h prime of x. You've probably done it already as I was jabbering away over there. H prime of x is 3x squared minus 12x. Okay, we're going to take this polynomial. We're going to set it equal to 0. Because it's a polynomial, we know that it always exists, so we don't have to worry about any values where the first derivative does not exist. We just got to figure out when the first derivative is equal to 0. What should we factor out of this polynomial? Sounds good. Let's take out a 3x. And if we take out 3x, then we have x minus 4 left over, and that's equal to 0. Excellent. We have ourselves a product, which is equal to 0, so we're going to cover them up one at a time. Let me put down the orange marker. If we cover up the 3x, we see that one of our critical values is 4. And if we cover up the x minus 4, we see that the other, there we go. We see that the other critical value is x equals 0. Right? So x equals 0 and x equals 4. Okay, those are our two critical values. And could we place these two on a number line and then do the plus minus chart? Absolutely. And that's one way to figure out whether these two critical values are relative max, relative min, or neither. Let me give you another option. The second derivative test says, well, if you go to the second derivative and you plug these critical values in, depending on your result, you can determine what the critical value is. Now let's think about this from a geometric point of view for a second. We have the derivative is equal to 0. We know that the derivative is the slope of the tangent to the curve at a point along the way. Hey, okay, so it's the slope of the tangent line, which means that if we were to draw a tangent line, the slope would have to be horizontal. All right, horizontal lines have 0 slope. We just found out when the derivative was equal to 0. Let's think about those pictures for a second. If there's horizontal tangent lines going on, this is going to be one of 3 cases. Case number 1 is a situation like this, where we have a hill, and at the top of the hill, we have ourselves a horizontal tangent line. Case number 2, we have ourselves a valley, and at the bottom of the valley is a horizontal tangent line. And then case number 3 has multiple versions. It can look like so, or it could look like so. But basically, in both cases, we have a horizontal tangent line just for a moment, but the function was increasing before and increasing afterwards, or decreasing before and decreasing afterwards. And in both of those cases, we have neither a max nor a min, just a horizontal tangent line. It's a critical number, nothing happens there. Classic example of this is the function y equals x cubed. There is a horizontal tangent line that actually looks a lot like this, right at the origin. Okay, but it's neither a max nor a min. Okay, well, let's think about this for a second. What do you notice about this drawing that I have right here in terms of its concavity? Exactly, it's concave down. Okay, this is concave up. This changes from concave down to concave up, and this version changes from concave up to concave down. So the concavity changes here. These are points of inflection. Okay, but the concavity does not change here. So let's talk about when a function is concave down. A function is concave down when the second derivative is negative. Exactly. So if we know that we have a horizontal tangent line at 0 and 4, and if we check the second derivative at these values, if the result is a negative value, that means that the second derivative is negative. But the first derivative is equal to 0. And a negative second derivative means our function must be concave down, and the 0 in the first derivative means that we must have a horizontal tangent line, which means we're talking about this situation right here, which means that the critical number will be a relative max. Right, that was a lot to go through. Let me talk about it quickly from the other side here. if we plug these values into the second derivative and we get a positive result, well, that means a positive second derivative is a concave up curvature. But at the same time, we know that there would be a horizontal tangent line at that point. Okay, so there's our horizontal tangent line. Concave up, horizontal tangent line means that we must have a relative min at that point. So if we check the value of the second derivative at those points, the concavity from there, and you can't actually be concave up or down at a point, but it's just it's a quick little synopsis. You can determine whether we have a relative max or relative min, or in the cases like these, neither. So let's go ahead and do that. We need to find h double prime of x, and that's why I picked this polynomial. It's a nice, quick second derivative to get. Second derivative we see here will be 6x minus 12. Okay, and I'm not interested when the second derivative is equal to 0. All I want to do is I want to plug the two critical values into the second derivative. So if we plug in 0, we have 0 minus 12, which is definitely negative. All right, it's definitely less than 0. So we have a situation like this: a negative second derivative and a horizontal tangent line, which means that at x equals 0, we are going to have a situation like this, which means that this is a relative max. Okay, x equals 0 is a relative max. Let's plug in 4. H double prime of 4, well, that's going to be 24 minus 12. 24 minus 12 is 12. 12 is greater than 0. So we have a situation where the second derivative is positive, and that horizontal tangent line tells us that 4 is going to be a relative min. Okay, so we can classify, if we go back to the problem, it says find all critical values of h. We did that. We got x equals 0 and x equals 4. Okay, and determine if each value is relative max or relative min or neither. Well, we have a relative, what do we say for 0? 0 is a relative max. All right, and 4 is a relative min. And again, if you're talking about the reason why, x equals 0 is a relative max because f prime of 0 equals 0, and f double prime of 0 is the situation that we talked about, negative. Okay, the first derivative at 0 is equal to 0. The second derivative at 0 is negative. That produces a relative max. Reason for, get that down there, give it a little more space. Reason why x equals 4 is relative min, because f prime at 4 was equal to 0, and f double prime at 4 was positive. So that's our reasoning. The second derivative test tells us that the results will be as such. So it's another test that you can use. You don't have to. You can do everything on the AP Calculus exam using the first derivative test. It's another way to go about it.